Hi, the next convolution I want to show you is that of the geometric random variable. So let me start off this one by refreshing the argument we made about negative binomial. So the negative binomial random variable was waiting time for the R success in independent trials. And we said that the first success comes after geometric time, then the second success after the first one comes after an independent geometric time again, and then the next one comes with geometric times, and so every success comes at geometric intervals. And if you look at the sum of the first R geometrics, that will give you the position or waiting time of the R success. And so we argued before that adding up independent optimistic geometrics R times will give us exactly the negative binomial. Okay? So the probabilistic or combinatorial argument from before was, so from the definition, let's say this, from the setup, the definition or setup of the random variables, we know already that the R-fold convolution of geometric P is negative binomial of parameters R and P. Okay, so again, this line here, which says that add up R independent optimistic geometrics and you get negative binomial, that exactly is the same statement as the R-fold convolution of these optimistic geometrics is negative binomial of parameter RP. Okay? Let's prove this. Let's suppose that we don't know this probabilistic stuff behind it. Let's prove this analytically. Let's prove this using formulas and convolutions. Okay? So what is the exact statement? Here is the exact proposition, if you wish. Proposition: let X be negative binomial of parameters Rp. Let Y be let's just take a geometric of the same parameter P, that's important, the parameters P must agree, independent, okay, and let's convolve these distributions. So then, if I look at the sum of x plus y, it is going to be negative binomial of parameters R plus 1 and P. So what I'm doing here with this proposition is essentially an inductive step on the way of proving this statement. So what is going on here really? What is going on is that I claim that in order to prove that the sum of R geometrics is negative binomial, it's enough to prove that taking some number of negative binomials and adding one more geometric will lead to a negative binomial of increased R parameter by 1. Because now, if we know that, so we're going to prove that, but before proving that, if we know that, then negative binomial of parameter 1 and P is of course geometric, just adding up one of these guys. Or if you want to look at this mass function, when R is 1, anything choose 0 is 1, q to the q minus 1, p to the r is exactly the p to the 1. Yes, R is 1. So q to the k minus 1 and p to the 1 is exactly the geometric mass function. So when we have 1 for the R parameter, then this is just optimistic geometric P. Okay, so that kind of starts the induction. And then if we want to find out the sum of y1 and y2 and yr, as we had this before, if we want to find out the distribution of that, and we know the analytic proof of that kind of this inductive statement, then we could say that this guy here is negative binomial of parameter 1p. This is geometric, so if I look at the sum of these two, according to the proposition, it's going to be negative binomial again with an increased parameter. So these two would be negative binomial of parameter 2p. Add the third one. So then y1 plus y2 plus y3. Since y1 and y2 is negative binomial of parameter 2, if I add the third one, it's going to be negative binomial of parameter, so this was negative binomial 2. According to the proposition, I have to increase this by 1, so that's going to be 3, and so on. And so you can go up in an inductive manner to prove that this is the negative binomial of parameters r and p. Okay, so if we prove this proposition here, then in an inductive fashion, we actually prove that the sum of R geometrics is negative binomial. And of course, in the same way, we prove that the sum of negative binomials is also negative binomial. If I look at y1 plus y2 plus yn plus yn plus 1 plus and so on, and yr, okay? Or, well, let's use n plus m here. Let's use n plus m, so that we have n of them and we have m of them. Then on one hand, we know that this is negative binomial of parameters n plus m r, according to this argument here. On the other hand, we know that the first bit, these guys, together form a negative binomial of parameters n and, oh, this is p, n and p. These guys together form a negative binomial of parameters m and p. And so and of course they are independent, because the first n is independent of the second m. So what that proves is that we have the convolution of negative binomial np and mp as negative binomial n plus m and p. Okay? So once you prove this inductive statement here, that adding a geometric, independent geometric to a negative binomial is negative binomial again with an increased parameter, once we know that, and that's what I'm going to do in a second, then we, in an inductive fashion, we can conclude that the sum of any number of optimistic geometrics is negative binomial, and the sum of negative binomials, independent of course, is again negative binomial. Okay? It's important that the p parameter is all the same all over this argument. Okay, so what I'm going to do now is to actually prove this. Okay, so we have this proposition, we want to prove this in an analytic fashion. And let's see how that goes using the convolution formulas. Okay, so again, we want to, so let's prove the proposition. So let's prove that if I want to convolve a negative binomial, so again, x is negative binomial. Now you see that. So I'm going to prove the proposition. So if x is negative binomial of parameter rp and y is negative binomial of parameter 1p, but really what I want to say here is that it's optimistic geometric of parameter p, independent, then, so that's what I want to prove, then x plus y is negative binomial. I'm just repeating the statement now of parameter r plus 1 and p. Okay, that's what I want to do. That's this proposition here. Just repeat it. Okay. What is the mass function of x plus y at k? usual business. It's going to be an infinite sum, as usual, from minus infinity to infinity of the mass function. So this time I want to use x at j and y at k minus j. I'm free to do it in either order. The reason I want to do it this way is that negative binomial is more complicated than geometric. So x has a more complicated mass function. It's probably easier to plug that j in there rather than k minus j. So this is the sum on j, and I'm going to see where this sum goes to and from. Okay, so negative binomial mass function at r and of r and p at parameter parameter r and p at point g. So what is that? Okay, so we're looking at the r success in j trial. So the first j minus 1 trials must have r minus 1 successes. These are the number of orders we can order them. We have the success probability raised to the r's power because we want r successes, and we want a total of j minus r failures because we want the j's trial to see the r success, and so we have this many failures beforehand. So this is that. And then we have to multiply this by the ordinary optimistic geometric mass function of y at k minus j. So that gives me q to the k minus j minus 1 times p. Okay? And I have to be very careful where j goes from and to. Where j goes from and to. Now, notice that this negative binomial j tells me that j has to be at least r. So I am going to start this off from r, and this tells me, this geometric tells me that k minus j has to be at least 1. So j has to stop before k. So I'm going to move this up to k minus 1 only. And clearly what I'm doing here is k at least r plus 1, because x is at least r and y is at least 1. So if k is smaller than r plus 1, then the thing is just 0. In that case, the sum is empty, and indeed empty sums are defined to be 0. Okay. So let's see the power of p. The power of p is simple, is just r plus 1. Let's see the power of q. Now the good news is that my summation variable j actually cancels out upon the power of q. So q can be factored out of this sum as q to the k minus 1 minus r, or if you want k minus r minus 1. Okay? And what's left is the sum from r to k minus 1 of j minus 1 r, choose r minus 1. Okay. What do I want? What I want is that this thing, the mass function of x plus y at k, is the negative binomial mass function of parameter r plus 1 and p at k. Now, what is that mass function? So I want the r plus first success to come at the k's trial. So I need a total of r plus 1 successes, k minus r plus 1, or if you want k minus r minus 1, total number of failures, and those are already here. And I want all possible orders in which I can arrange these successes and failures. So I want this thing, I want this whole thing to be q to the k minus r minus 1, p to the r plus 1, this is all fine, multiplied with the binomial coefficient of the number of orders of the previous r previous r successes in the previous k minus 1 trials. So as soon as I prove that this is k minus 1, choose r, then I'm done. As soon as I prove this is k minus 1, choose r, then together q to the k minus r minus 1, p to the r plus 1, k minus 1 choose r is exactly the negative binomial mass function of parameter r plus 1p at k. So that's what I want. Okay, so from now on I want to show that this is true for any k at least r plus 1. I'm going to do that by induction. Okay, so that's what I want, and let's do this by induction. There is quite a number of induction steps in this argument. Let's do this by induction. By this I mean this, what I want. Okay, so the smallest value k could be is of course r plus 1. If k is r plus 1, what is it that I want? I want a sum from r to r plus 1 minus 1, k is r plus 1, of j minus 1 choose r minus 1. What I want is that this is k minus 1 choose r. K minus 1 is r plus 1 minus 1, choose r. Okay, now what is the left hand side? The left hand side is j goes from r to r. That's only one value, j equals to r. Is it true that r minus 1 choose r minus 1 is the same as r choose r? And the answer is of course true, because both are 1. Any positive integer choose the same integer is 1. There's just one way of picking everything from a set. Okay, so that's the starting point of the induction. And now let's assume that is true for k. Assume that what I want, this thing, is true for k. Of course, k is at least r plus 1. And let's show that it's going to be true for k plus 1 as well. So then, what is the statement for k plus 1? K, the sum goes from r to k. Instead of k minus 1, it goes to k. J minus 1 choose r minus 1. Is it the same as k choose r? Is it the same as k choose r? Okay, so let's see. Obviously, I'm going to separate this sum into the 1 to k minus 1 and the last term. What is the last term? The last term is when j equals to k. So I have k minus 1 choose r minus 1. Okay. Now let's use the assumption on the first sum. Notice that this first part here is of course the same as what I had in the inductive assumption. So let's use that by assumption I have k minus 1 choose r for the first part. So for this part. And I have k minus 1 choose r minus 1 in the second part. And now comes something called Pascal's identity. Which says that if you add up these two binomial coefficients, you exactly get k choose r. There are various ways to prove this. Of course, you can write out all the factorials and then you'll see it's true. There is also a combinatorial proof. Assume that you want to pick r objects out of k, and you look at all possibilities where the first object is chosen. So the remaining r minus 1 has to be picked from the remaining k minus 1. All possibilities when the first object is not chosen, namely all of your r choices need to be picked from the remaining k minus 1. These two together count the number of ways to pick r out of k. Okay? So by Pascal identity this is true. If this is true, that means that we prove that this sum up to k is equal to k choose r, which is exactly the same statement as what we wanted for 1 increased k. Increase k by 1, so you have k there, and k choose r there. So the inductive step is done. Inductive step is done. Okay, so that shows that what we want for the proof to be complete is actually true by induction, and so we conclude the proof because the convolution formula then just works, and we proved in an analytic way that adding a negative binomial and the geometric, if they are independent, results in a negative binomial with one increased parameter. And then by induction, as we already discussed, by induction this proves that the whole thing is true. Any number of independent geometrics of the same p parameter is going to be summed up to the negative binomial distribution, and as a consequence the sum of independent negative binomials is negative binomial again.